Hello and a very good afternoon to Dr. Pasita. My name is Nufriza Amira binti Azmi and I'm with my friend Umi Natasha binti Kamaruzaman. We are from Group 10 and today we will be presenting about NF-kB and TNF.
Tumor necrosis factor, or known as TNF, is a multifunctional cytokine that plays an important role in diverse cellular events such as cell survival, proliferation, differentiation, and death. TNF is a protein consists of 157 amino acids and synthesized as membrane-bound protein (TNF) that is released by TNF converting enzyme mediated cleavage. TNF also involved in inflammation-associated carcinogenesis.
What is NF-kB? NF-kB is a short name of nuclear factor kappa light chain enhancer of activated B cell. It is not a single protein but a small family of inducible transcription factor that play an important role in almost all mammalian cells. NF-kB molecules are usually dimer. A typical structure of NF-kB is P50 to P65 dimer. NF-kB1 or A. The dimer formation is necessary for DNA binding. Two NF-kB monomer bind to DNA as a dimer. NF-kB also plays a key role in regulating the immune response to infection.
Okay, what is the function of TNF? Basically, TNF involved in activating distinct signaling pathways such as NF-kB and JNK. TNF also is known as double dealer because it can be endogenous tumor promoter such as TNF can stimulate cancer cell growth, proliferation, invasion and metastasis, and tumor agenesis. TNF also could be a cancer killer due to property of TNF in inducing cancer cell, thus render it potential cancer therapeutic.
Moving on to the function of NF-kB. NF-kB regulates many important cellular behavior, in particular inflammatory response, cellular growth, and apoptosis. The primary function of NF-kB is in the regulation of apoptosis. NF-kB predominantly prevents apoptosis in B cell and promotes B cell activation. There is also an opposite effect of NF-kB, which it can bring good and harm to the body. For the good side is it prevents apoptosis in hepatocyte, thereby enhancing liver regeneration. In contrast, it can also bring harm to the body by inducing apoptosis in the event of viral infection, such as an adenoviral infection.
TNF-inducing signaling pathway. In this pathway, it involves the binding of TNF trimer to the extracellular domain of TNFR1, and it will release protein silencer of that domain from TNFR1 intracellular domain. It will form a receptor proximal complex contain 4 important adapter protein, which is TRADD, TRAF2, RIP, and FADD. The activation of 4 adapter protein will lead to, firstly, FADD by caspase 8 will initiate to the protease cascade that lead to apoptosis. Second, TRAF2 recruits cellular inhibitory of apoptosis protein 1 and 2 to anti-apoptosis protein that also have ubiquitin protein ligase activity. And lastly, protein kinase RIP will activate the transcription factor, which is NF-kB. Next pathway is TNF-induced activation of NF-kB. First, it will start by activation of inhibitor of KB and kinase, IKB and IKK. During TNFR1 signaling, IKK is recruited to the TNFR1 signaling complex 1, which is consists of TRADD, TRAF2, and RIP. IKK is activated by RIP-dependent mechanism that involve MEKK3, TAK1, and TAB2. The activated of IKK phosphorylates IKB, which retain NF-kB in the cytoplasm. to trigger its rapid polyubiquitination followed by degradation in S26 proteasome. This process causes the NF-kB nuclear localization signal to be exposed, allow its nuclear translocation to promote transcription of its target genes. The transcriptional activity of NF-kB is further regulated by phosphorylation and acetylation, which modulate the DNA binding by NF-kB and interaction with transcriptional co-activator or co-repressor.
Next is the most crucial one, which is the NF-kB signaling pathway. The most frequently recognized NF-kB pathway are the canonical and non-canonical pathway. The canonical NF-kB pathway is activated by pro-inflammatory cytokines such as TNF-alpha and interleukin-1, T and B cell mitogen, bacterial liposaccharide (LPS), viral protein, and physical and chemical stress. A first step in the canonical pathway is the activation of transforming growth factor beta, TGF-beta activated kinase 1, which is called TAK1, which further activates the trimeric IKB kinase IKK complex that is composed of regulatory and NF-kB extension modulator NEMO or IKK gamma and catalytic IKK alpha and IKK beta subunit. The IKK complex then phosphorylate IKB at specific serine residue, which result in polyubiquitination and subsequent proteasomal degradation of IKB, followed by nuclear translocation of NF-kB, mainly the P50 or P65 heterodimer. The heterodimer then binds to the KB site and activates numerous genes that involve in inflammatory and immune response, including cytokine, chemokine, inflammatory mediator, adhesion molecule, and apoptosis inhibitor. In contrast to the canonical pathway that responds rapidly to signal from the diverse receptor, the non-canonical pathway specifically responds to a small group of receptors, including lymphotoxin beta receptor, which is called LT-beta-R, B cell activating factor belonging to TNF family receptor, which is called BAFFR, CD40, and receptor activator for NF-kB, which is called RANG. Upon binding, this receptor activates the kinase NF-kB inducing kinase NIK, which in turn phosphorylate and activate IKK alpha. Activated IKK alpha then phosphorylate P100 or LB heterodimer at the carboxy terminal serine residue of P100, resulting in processing of P100 to P52 and nuclear translocation of P52 or LB. Activated P52 or LB heterodimer then binds to the specific KB enhancer and subsequently activates transcription of its target gene.